Now we will look at some issues that you might encounter while dealing with threads. We will first be talking about semantics of fork and exec system calls. These are related still to threads because you can, for example, use fork or exec in a program that has multiple threads. So what happens in that case? We'll talk about signal handling, how signals are delivered to multi-threaded applications. You might need to cancel a thread you have started prematurely. Thread local storage are the things we're going to discuss in this video, and scheduler activation will be for the next videos. So let's first talk about the semantics of fork and exec. You already know what fork and exec do. But if you use fork in a process that has in a process that has multiple threads, what happens? In some Unix flavors, in some implementations of Unix, there are two versions of fork to decide whether all threads will be created or not. In POSIX, which is the most commonly implemented thread library, therefore also in Linux, only the thread that's calling fork function is duplicated. All other threads are dead. Now, this is something strange. I should explain what dead there is. Remember what fork does. In the case of fork, you duplicate the whole process with all its memory address space. You get a full copy of the process. The only difference was to the process that calls fork, it returns the process ID, the PID of the child process, and to the child process it returns the value 0. But all other things were copied as they are. And remember, the child process continues from the same statement. It's not starting from the beginning. It's continuing from the same statement. Now, when you do this operation, in the case of a multi-threaded process, this parent process has multiple, let's say it has 3 threads that are created. There's also the main thread, so it makes 4 threads. Now, when you create a duplicate of this, the new one will definitely have the main thread. It has to be there. Actually, not the main thread, but the thread that has called the fork. Typically, it is the main thread. But all other threads will not be created. That's why we're saying dead. But still, the execution, the program counter, will continue from the next statement. It's not starting from the beginning of main. So the child is in a strange position. Be careful with this. The child is now executing a statement before which 3 other threads should have been created. And if they failed, actually you would not have been here. But to the child process, it appears like those other threads mysteriously have died. So if the child process depends on the proper execution of those threads, you will have problems. So you should be very careful when you're dealing with fork, when you're using fork in processes that are multi-threaded. However, you can use some specific methods, like you can use pthread at fork and pthread set specific to deal with problems and avoid deadlocks. By the way, I didn't mention the deadlocks here. There is the problem of a possible deadlock with these when the child processes are not created, because it is possible that in the parent process the threads that were created, they acquire the lock because we want mutual exclusion. We don't. So this thread that was created, say, locked a record because it's currently updating it, and it has not released the lock yet. After it has completed a series of instructions, it will be releasing the lock. But when you do a fork, that thread will not exist. It is dead. But if you look at the data structures, that specific data structure is under lock. So it is locked, but it's not possible for it to be unlocked because whoever would be unlocking it is already dead. So this is just like you lock the door and throw the key in the sea. So there is no way to unlock it again. So it is possible that you may fall into a deadlock when these other threads are dead in the child process. Nothing will go wrong in the parent, but the child process may get deadlocked. To avoid this, you should be making use of functions like pthread at fork and pthread set specific that explain, that define what should happen if the thread is dead. So when the child process is created, these functions will take care of such cases to avoid the deadlocks. This was for the case of fork. For the case of exec, actually nothing is different. When you call exec, now it's not only that thread that calls exec is replaced by the code, but the whole process is replaced. Therefore, exec just performs as normal, as you would expect. Just a side note, not directly related with what we're discussing here, but you should still keep this in mind. Remember, when a process says fork, you're making a full copy, and then in most cases, not in all cases, but in most cases, a process that calls fork immediately calls exec. The reason you're creating the child process is typically, for example, to run another executable code. Then there is a strange, you're in a strange position. You're creating a child process, a new process that will be immediately replaced. So why did you copy everything? If you know that the child process will immediately call exec, instead of fork, you can call vfork. There's a v in front. And this vfork will not do that duplication. And after vfork, you should be using not exec or execl, but you should be using exec ve to execute, to exec that other process. And this performs much better. This is true in many Unix flavors. In the case of Linux, vfork is actually the normal fork, so it won't help. It won't harm, but it won't provide you improvements in using vfork instead of fork. It would be the same thing. What I explained about vfork and execv is not directly related to threads. This is true when you have threads or when it's a single threaded system. In all cases, what I said is valid. Now, how about signals? I have been mentioning signals to you often, but we didn't go in detail about signals. We'll have another video later about signals because that's an important concept. But in Unix, a signal is used to notify some process, either the current process or maybe another process, of something happening. That's why you signal it. So signal is actually a kind of a software interrupt. You're interrupting a process, but this interrupt is not caused by something in the typically hardware, but mostly it is due to something in the software. For example, you just want to inform another process, for example, the parent process, about the completion or the termination of its child process. So for that we send the sick child signal, whatever. There are different signals. Or, you know, when a process, for example, just gets locked and you cannot stop the program, you cannot it doesn't progress at all. So what we do in that case is we try to kill the process. So in that case, we're sending the sick kill signal to the process. So signal is generated typically by some particular event. When something happens, the signal is created. And to send a signal to a process, you call the kill function. You give the process ID of the process which needs to be informed, which will be receiving the signal, in other words, and also the signal number that corresponds to the signal you want to send. The signal is handled by one of the two signal handlers. One is a default signal handler. This is actually system-wide signal handler for that specific signal. So when that signal is received, the kernel knows what to do. So the kernel has the handler for that, and you're just calling the same function. Or if you wish, you can write your own signal handler and modify your signal table, saying if this signal occurs, don't call the default signal handler, call my signal handler, this function. So you write a function and you associate it with that specific signal. And it works only for that process, not even for all your processes. It works only for that process. There is actually a third option, but we cannot call it signal handling because that is ignore. You might say, if this signal happens, you don't need to inform me. I will not do anything. You don't do anything either. So it's not even the default handler. It just says, just ignore it. We don't care about that. Okay? Why? As I said, you can write your own signal handlers and override the default. If you have a single threaded system, the signal will be delivered to that process. What happens if you have a multi-threaded process? We'll just come to that in the next slide. But before going into that, let me mention one thing. For example, you know, to stop a process, you can press Control C. Okay? But you might have realized that in some processes, when you say Control C, the process will immediately terminate. But it is also possible, and you might have seen such programs earlier, it is also possible that the when you press Control C, the process says, the user wants to terminate, and I'm terminating. Now, this is a good practice, by the way. We call this graceful termination. That means rather than the program suddenly crashing because Control C has been pressed by the user, if you detect that Control C is pressed, now you, for example, let's say if you had open files, you close the open files. If there was another process that was expecting input from you, let's say over a pipe, you write a message to the pipe saying, sorry, I have received user break, that's what control C is. I have received user break. The user wants to break me, which means terminate this process. So I'm just terminating myself. Goodbye. So you inform the other party rather than suddenly disappearing. You might need to take some actions about the files, about the databases, to provide their consistencies. You do all these. You might even want to, for example, if you have a logger, you might want to put a log in the logger saying, I'm terminating, but it's not that I crashed. The user wanted me to terminate. This is important because later when we look at the logs, we will observe that suddenly this process, while it was working and writing logs, it has restarted. Why did the process start from the beginning? You would think that suddenly the program crashed. No, it didn't crash. It was the user who requested the program to terminate. So you can take care of all of these and then terminate, for example. Or in the case of the children terminating, when you receive sick child, you would be interested in why the child process terminated. Was that a regular termination or did it crash? If it terminated, did it return 0 for successful termination because it has come to the end of the main method, and there you say maybe return 0 to show regular termination, or did it return -1 saying I cannot open the I cannot find the configuration file, or -2 like I can find the configuration file but I don't have read permissions, or other things. You can learn all these as a parent process. And also, if necessary, if there is a problem, like there was, let's assume, a problem with the configuration file, you regenerate the configuration file, or if it was a permission problem, you fix the permission problem and then create the child process once again. So it's important to know all that. Anyways, that's why the signals are used. But once again, the question is, what happens if we try to send a signal to a multi-threaded process? Where should that signal be delivered? Should it be delivered to the thread to which the signal applies? Question mark. How do we know that thread? Do we know if there is such a thread? Or do we deliver it to every thread in the process? This is not, by the way, possible because the signals occur once. So even if you deliver it to all threads, when one of them receives a signal, the others will not be able to receive it. Or deliver the signal to certain threads in the process. That is possible. Like you might say this thread is responsible for such signals. This thread is responsible for others, whatever. Or you can have a specific thread that's receiving all signals for the process. So all other threads will just ignore the signal, and only that specific thread will enable the signals and also define their signal handlers. So it will take care of that. POSIX provides a specific function named Pthread Kill, which allows you to send a signal to a specific thread by using the thread ID. Now, it is possible that you create a thread and later you change your mind before the thread completes. This is very frequently used in, for example, interactive programs. Okay, like let's say you want to search for a file which has a specific word in the file name or maybe in the content. You start a search and this software starts scanning all files under a directory tree, which is a quite long process maybe, if the directory tree is very large and there are many files in it. But at some point, you find what you were searching for. Now you want to stop it. You already found what you were searching for. You don't need to look at the rest of the directory tree. But if that task of searching the directory tree was given to a thread, it will say, no, I just got my duty. I have to fulfill it to the last file. No, that shouldn't be the case. So in that case, you would like to cancel that thread because you already got what you want, or maybe you don't want it anymore. You change your mind. There is a problem. Anyways, for some reason, because of the logic of the program, you might want to cancel a thread you have started before the thread itself completes. Such a thread, when you want to cancel a thread, that will be called the target thread. And there are two ways to cancel it. You can have an asynchronous cancellation. That means you just say terminate and the thread immediately terminates. Or deferred cancellation, in which case the thread, the target thread, once in a while, in a periodic manner, specifically when it comes to, for example, the end of the loop, it's always iterating, whatever, at specific points in time, it's looking into notifications telling that it was told to cancel itself. So in that case, the thread has received a cancel request, but it doesn't immediately cancel, as in the case of asynchronous cancellation. It continues what it was doing. And when it says, if someone has requested me to cancel, I may at this moment. So it checks if there is something like that. If so, it will. If not, it will just continue. Okay, so this one is somehow synchronized, as you can see, like at the end of each iteration. Okay, so that's why this is a synchronized way of cancellation, the deferred cancellation, and that's why the other one is called asynchronous cancellation. So in POSIX, as you know, you can create a thread using the Pthread create, and to cancel it, you just use Pthread Cancel and give the thread ID. And then you can wait for this thread to cancel itself, and you will have a join there. When you want to invoke cancellation, but you might want to invoke cancellation, but the actual cancellation might depend on the state. Like, it is possible that a thread completely disables cancellation. The thread later can again enable cancellation. But for example, if the thread is doing something that will affect the integrity of the data of a file, of a database, it might disable cancellation, because it's like, you either don't ask me to do something, or if you do, then you should wait until I complete this. So the thread may disable it. The thread may say, okay, you can ask me to cancel, but I will check when I want to. Or it might say, if you need me to cancel, just tell me so and I will do it. So if thread has cancellation disabled, the cancellation remains pending until the thread enables it. It might not enable at all, pay attention. But if it enables, it will see an earlier cancel request. It's not like any cancel request while I had disabled it are lost. That's not the case. It will just wait there, still hoping that at some point the thread will enable cancellation, though it's not guaranteed. The default type is deferred, and the cancellation only occurs when the thread reaches the cancellation point, if it's the deferred case, at that point the thread may make use of the pthread test cancel function to see if anyone has requested the thread to cancel. And if so, it can now trigger a cleanup handler that will do the cancellation in a proper manner. Like you may want to again close files, take some actions before cancellation, whatever, you do all these. On Linux systems, the thread cancellation is handled through the signals we mentioned. So finally, the thread local storage. The threads have something called the TLS, the thread local storage, that will allow each thread to have its own copy of data. Now, this is different than regular local variables. It's useful when you do not have the control over the thread creation process, because this actually works just like the static variables in C. Remember, the static variable is like a local variable, but from invocation to invocation, every time you call that function, the static variables remember their previous values from the previous invocation. So similar is done here. Actually, the TLS is defined as static data, but it's unique to each thread. As I said, it's different than local variables, because their lifetime would be actually a single invocation of the function. But the TLS is visible and it is alive from invocation to invocation. So the lifetime of the TLS is the whole process execution time rather than the function invocation.